In 1846, French mathematician Urbain Le Verrier carefully investigated the movements of our planets. His attention was drawn to the orbit of Uranus. Le Verrier noticed a mysterious inconsistency between his calculations of Uranus' orbit and the actual observations. He rechecked and fine-tuned his calculations over and over again. But no matter what he did, Uranus was always in a position different than his calculations predicted. How could this discrepancy be explained? Eventually, Le Verrier proposed a bold hypothesis. He predicted the existence of a yet undiscovered eighth planet based solely on his observations of the movement of Uranus. The gravitational pull of this undiscovered planet could explain the irregularity in Uranus' orbit. This unknown planet would have to be located way beyond Uranus, far from the Sun in the outskirts of the planetary system. Le Verrier sent his calculations to the German astronomer Johann Galle. In his letter, he asked Galle to search for the so far undiscovered eighth planet. That very night, Galle pointed his telescope in the direction calculated by Le Verrier, and indeed, Galle saw a speckle of light not indicated on his stellar map. Galle had directly observed Neptune, the eighth planet in our solar system, precisely where Le Verrier had predicted. What a terrific success Le Verrier's gravitational calculations. Scientists continued to refine their understanding of gravity. Today, we are able to precisely calculate the motion in the universe using more modern theories, such as Einstein's theory of general relativity. However, the depths of our universe hold an exceptional mystery.
A merry-go-round. You have to be careful not to fall off. The faster the merry-go-round turns, the tighter you have to hold on. At its perimeter, the forces acting on your body are stronger than closer to the center. When standing further out, you are more easily thrown off, and the merry-go-round must turn more slowly. With a merry-go-round, we have a rather intuitive understanding of this concept, but the same holds true in the universe.
In our solar system, all planets orbit the Sun. The exact same principle that applies to a merry-go-round also applies here. The faster the planets orbit, the stronger they must be drawn to the Sun. It is the gravity of our Sun that holds the planets towards it and keeps them in their orbits. A planet further from the Sun experiences a smaller gravitational pull than one closer to the Sun. Therefore, to stay in orbit, a distant planet must move more slowly, or it would be flung out of our solar system. This is just the same as with the merry-go-round. The children standing at the edge of the merry-go-round can only maintain their position at a lower speed. This correlation between distance and speed was identified in the 17th century by Johannes Kepler. It is called Kepler's laws of planetary motion. Shortly thereafter, Isaac Newton was able to mathematically explain this correlation using his law of universal gravitation. And about 200 years later, Albert Einstein was able to fine-tune this relationship even further using his theory of general relativity. Today, using these laws, we are able to predict the motions of celestial objects such as planets, moons, comets, asteroids, and satellites with exceptional accuracy.
The Earth, the Sun, our solar system are part of a much larger structure. The Milky Way, our galaxy. The Milky Way is a spiral galaxy. Hundreds of billions of stars orbit around one common center. We would expect that the rotation of the Milky Way also follows Kepler's law. The farther away stars are located from the center of the galaxy, the slower they travel. But that is not the case. Instead, all stars orbit around the center with equal speed. The speed of the stars is independent from their location from the center of the galaxy. Our Milky Way is rotating faster than Kepler's laws would allow. How is this possible? Our Milky Way is not the only galaxy to show this behavior. Every spiral galaxy rotates the same way. Their stars always travel with equal speed around the galaxy's center. How is it that stars can move so fast without the galaxies breaking apart? What keeps the stars in their orbits? The answer is an additional force, a kind of glue that holds each galaxy together. This is our first piece of evidence that there must be more matter in our universe than we can see. It is the gravity of this additional matter that holds galaxies together. No matter what wavelength we look at the sky, invisible light, infrared or ultraviolet, radio waves or X-rays, we are not able to see this additional matter. It remains concealed. We cannot see or feel this matter. No detector has ever been able to observe it directly. We therefore call it dark matter. The gravity from dark matter is what keeps the stars in their orbits. Dark matter acts like a glue. Its gravity keeps the galaxies together. Galaxies are loaded with it. In fact, galaxies contain 5 times more dark matter than normal matter. We know it exists, but we have no idea what it's made of.
The European Center for Nuclear Research, CERN, in Geneva, Switzerland. Home to the largest and most powerful particle accelerator in the world, the Large Hadron Collider, LHC. Immense in size, the Large Hadron Collider is a 16 miles or 27 kilometers long circular tunnel. It reaches from Switzerland across the border into neighboring France. From technicians and scientists, from tools and materials, everything is brought underground through service shafts, such as this one, reaching 30 stories underground. In this tunnel, hydrogen nuclei are accelerated nearly to the speed of light and set on a collision course. Each second, more than 1 billion hydrogen nuclei collide. In the extreme conditions of these collisions, new particles are created. The particle accelerator itself is only one part of the experiments being conducted at CERN. The point where the hydrogen nuclei collide is surrounded by huge detectors, each of them the size of a multi-story building. Here we are moving through one of those detectors, the Compact Muon Solenoid, CMS. This highly complex machine detects each newly created particle with all its properties. This produces a tremendous amount of data, more than 1 gigabyte each second. The particles created during each collision can be identified only through elaborate analysis. To meet this challenge, large international collaborations with more than 2,000 scientists from all over the world examine this data for traces of yet undiscovered particles. The Higgs particle was recently discovered using this method. And similarly, scientists at the Large Hadron Collider are searching for dark matter particles in their data.
We return to outer space to continue our quest for dark matter, far away, well beyond our Milky Way. Galaxies do not exist in isolation. Rather, they group together with other galaxies to form galaxy clusters. Such galaxy clusters are found everywhere, near and far, with each cluster containing different numbers and types of galaxies. With ordinary telescopes, scientists can only see matter that radiates visible light. This is just a tiny fraction of the total matter found in galaxy clusters. The Chandra X-ray telescope can see beyond visible light into the X-ray range of this spectrum. With this telescope, diffuse hydrogen gas becomes visible. Shown here in red, this gas fills up the space in between galaxies and comprises significantly more mass than all shining stars combined. Using a technique called gravitational lensing, it can be shown that indeed, most mass is located in this diffuse gas. Gravitational lensing allows us to basically weigh galaxy clusters. If we examine images of galaxy clusters carefully, we can see small arcs. These are distorted images of galaxies that are located far beyond the galaxy cluster. The gravity of the galaxy cluster has bent the light from the galaxies in the background. This effect is called gravitational lensing. The more massive a galaxy cluster is, the more it will bend light from the galaxies in the background. Therefore, we can calculate the mass of a galaxy cluster as well as its distribution using the observed gravitational lensing. The Bullet Cluster is located in the southern sky constellation Carina. Here, two galaxy clusters passed through each other about 100 million years ago. Even within galaxy clusters, individual galaxies are very far apart and rarely collide. Galaxy clusters simply move through each other. A very different behavior is observed in the diffuse hydrogen gas within the galaxies, shown here in red from an X-ray image. While both gas clouds collide, friction slows them down. A wake forms, easily visible in the cluster on the right. This shape gave the Bullet Cluster its name. As the hydrogen gas slows down, it lags behind the galaxies. Today, 100 million years later, we observe two clouds separated from the galaxies. We would expect that most of the mass is located in those gas clouds. This can be tested with gravitational lensing. However, this leads to a big surprise. Most of the mass, highlighted here in blue, is found near the galaxies. There is 5 times more mass where the galaxies are, compared to what we can see in the form of stars and diffuse hydrogen gas together. This invisible mass is dark matter again. Apparently, dark matter just kept moving without being influenced by the collision at all. It passed through itself without interacting or slowing down. No known form of matter shows such a behavior. Dark matter has to be a completely new, unknown form of matter. We learn something about dark matter without ever having seen it.
About 250 miles, or 400 kilometers above Earth, the International Space Station, ISS, an impressive example of international collaboration. The United States, Canada, 11 European countries, Russia, and Japan built and operate the space station together. Naturally, radioactive particles from outer space constantly bombard Earth. We call these particles the cosmic radiation. Since 2011, the Alpha Magnetic Spectrometer, AMS, located on the International Space Station, is being used to study this radiation. This detector is similar in complexity to the detectors located in the Large Hadron Collider at CERN. But additionally, the Alpha Magnetic Spectrometer is located in Earth orbit. At the Large Hadron Collider at CERN, scientists attempt to create dark matter particles from collisions of hydrogen nuclei. With the Alpha Magnetic Spectrometer, in contrast, scientists attempt to search for the inverse process. They search for particles that are created when dark matter particles collide with each other in outer space. The main difficulty is to differentiate dark matter signals from other signals, such as those from black holes or neutron stars. This is one of the many challenges scientists are currently investigating.
The Mount Wilson Observatory in California. In the 1920s, building on the work of astronomers before him, Edwin Hubble observed the motions of galaxies. But he made one of the most momentous discoveries of his time. The universe is expanding. All galaxies are moving away from each other. So, if we, just as a thought, turn back time, this implies that someday, in the past, the universe was densely packed. We say the universe started with a hot Big Bang. Since then, space has continuously expanded, causing the universe to cool. The heat remaining from the Big Bang is still out there. We call it the cosmic microwave background radiation. This is how the universe looked when it was only 300,000 years old. Everything was exactly the same in each direction, completely void of structure. Today, we measure this radiation with sophisticated satellites. It is only by looking extremely closely at this radiation that minute temperature differences become visible. The young universe was a rather dreary place. In contrast, our universe today is teeming with complex structures, galaxies, planets, nebulae. But how did they evolve? Today, we are able to simulate this fantastic evolution with the help of supercomputers, shown here in a time lapse. The brighter an area, the higher the concentration of matter. As a result of gravity, matter clumps together. First, smaller structures form. Like a magnet, the gravity of those early galaxies pulls more and more matter towards them. The galaxies grow larger and larger. Slowly but surely, the universe develops into its present-day configuration. Gigantic structures more than 100 million light-years across permeate the universe like filaments in a sponge. Those tiny fluctuations that we observe in the cosmic microwave background radiation, emitted shortly after the Big Bang, had to clump together rapidly in order to form the huge structures we observe today. This requires an enormous amount of gravitational pull, the gravity of dark matter. We can model the observed universe with astounding accuracy in computer simulations. These simulations give the correct picture even when all they simulate is just dark matter. The evolution of the universe thus gives us another piece of evidence for the existence of dark matter. We only see the stars glowing. Like lanterns, they hang on the cosmic scaffold made of dark matter. But for the evolution of the universe, they are irrelevant. Galaxies, stars, and their planets, and everything that is happening on those planets, all these incredible actors have no major role on the magnificent stage of the cosmos.
We are flying through the Milky Way with our spaceship Earth. In doing so, we pass through the vast amount of dark matter that fills the Milky Way. Using sophisticated experiments, scientists are trying to capture individual particles from this headwind of dark matter. Discoveri, Italy, a sleepy mountain village east of Rome, located in the middle of the Italian Abruzzo Mountains. This region is not a tourist attraction. Only a few will know of it, perhaps for its red wine, Montepulciano d'Abruzzo, for its saffron or its truffles. Or perhaps for the beautiful mountain landscape. You would be surprised to find one of the most important research facilities engaged in the search for dark matter, far beneath the extensive hiking trails of the national park, in the heart of the Gran Sasso Mountain. In the 1980s, a highway tunnel more than 6 miles, or 10 kilometers long, was dug into the mountain to establish a highway from Rome across Italy to the Adriatic Sea. This was an opportunity to build the world's largest underground laboratory, the Laboratorio Nazionale del Gran Sasso. This lab is located halfway into the tunnel in the middle of the mountain. A maze of corridors, tunnels, and gigantic halls. Various experiments are located here, all for the same reason: to be shielded from other environmental influences, especially from cosmic radiation. While cosmic radiation is the key signal for the alpha magnetic spectrometer in space, on Earth's surface it is an annoying source of background for these experiments. But 1 mile beneath the Gran Sasso mountain, hardly any of it is left. This is why it is a great location to look for even the weakest signals from various particles. It is the perfect place for the most sensitive detector in the search for dark matter, the xenon detector. A water tank, 30 feet or 10 meters in diameter, screens out all kinds of natural radioactivity from the surrounding rock. A cryostat at the center of the water tank holds liquid xenon. More than 3 tons of this noble element are very carefully monitored by highly sensitive cameras looking for traces of faint signals. This is why this is a great location to look for even the weakest signals from various particles. The scientists involved in this experiment hope to be able to spot a glimpse of dark matter particles caught in their xenon detector.
The structures we observe in the universe today only formed because of vast amounts of dark matter. Gravitational lensing shows us that galaxy clusters are actually heavier than initially thought. And dark matter holds the rapidly rotating galaxies together. These are only 3 examples of a long list of independent observations that all lead us to the same conclusion. The universe is dominated by dark matter. The rest? It's just a cherry on top. So we know that dark matter exists. But what is it made of? What is dark matter? We are in a similar situation today as once Johann Galle almost 150 years ago. Once again, gravity shows us the existence of new, yet unknown matter. But today, a variety of technologies are available to explore this cosmic secret. We can search for various particles that originate from dark matter using the alpha magnetic spectrometer and other telescopes. We can try to detect dark matter particles using dedicated experiments far underground. And we can even attempt to produce dark matter particles in accelerator experiments. But the question still remains: which experiment will be the first to detect dark matter particles? From the beginning of time, we observed the cosmos at night. And from the beginning of time, we suspected that the universe was teeming with unknown wonders. Today, we look at the starry night. And for the first time in our history, we know that the universe is commanded by unseen matter. It is up to us to answer this challenge. It is time to be curious.
In our solar system, all planets orbit the Sun. The exact same principle that applies to a merry-go-round also applies here. The faster the planets orbit, the stronger they must be drawn to the Sun. It is the gravity of our Sun that holds the planets towards it and keeps them in their orbits. A planet further from the Sun experiences a smaller gravitational pull than one closer to the Sun. Therefore, to stay in orbit, a distant planet must move more slowly, or it would be flung out of our solar system. This is just the same as with the merry-go-round. The children standing at the edge of the merry-go-round can only maintain their position at a lower speed. This correlation between distance and speed was identified in the 17th century by Johannes Kepler. It is called Kepler's laws of planetary motion.
Are stronger than closer to the center. When standing further out, you are more easily thrown off, and the merry-go-round must turn more slowly. With a merry-go-round, we have a rather intuitive understanding of this concept, but the same holds true in the universe. A merry-go-round. You have to be careful not to fall off. The faster the merry-go-round turns, the tighter you have to hold on. At its perimeter, the forces acting on your body
far from the sun in the outskirts of the planetary system. Leverrier sent his calculations to the German astronomer Johann Galle. In his letter, he asked Galle to search for the so far undiscovered eighth planet. That very night, Galle pointed his telescope in the direction calculated by Leverrier, and indeed, Galle saw a speckle of light not indicated on his stellar map. Galle had directly observed Neptune, the eighth planet in our solar system, precisely where Leverrier had predicted. What a terrific success Leverrier's gravitational calculations. Scientists continued to refine their understanding of gravity. Today, we are able to precisely calculate the motion in the universe using more modern theories, such as Einstein's theory of general relativity. However, the depths of our universe hold an exceptional mystery. In 1846, French mathematician Urbain Le Verrier carefully investigated the movements of our planets. His attention was drawn to the orbit of Uranus. Le Verrier noticed a mysterious inconsistency between his calculations of Uranus' orbit and the actual observations. He rechecked and fine-tuned his calculations over and over again. But no matter what he did, Uranus was always in a position different than his calculations predicted. How could this discrepancy be explained? Eventually, Leverrier proposed a bold hypothesis. He predicted the existence of a yet undiscovered eighth planet based solely on his observations of the movement of Uranus. The gravitational pull of this undiscovered planet could explain the irregularity in Uranus' orbit. This unknown planet would have to be located way beyond Uranus.